Serious answer problem.
This is for me.
Okay.
So I would expect.
Yeah.
Not as much support.
Yeah.
So I expected concentration.
Yeah.
Obviously, same thing can be applied or can be said about the steel.
Sure.
But I noticed that when I applied, so I'm trying to see right here, like right here, the circular time.
Okay.
Where I applied it to the-
Yeah.
So my thinking was the reason why both sides aren't as heavily as affected is because here you have a drum striking downwards with the middle of the blade. But also you have a force that's acting parallel across the negative z direction. So you're having a force that's like this at the same time. So I figured it's somewhat reasonable because, well, then again, at the same time, I don't see how it's reasonable because I would still expect to see a decent amount of stress concentration right here, like at least some of that, but it's not. So
That's stress with the definition.
definition.
Okay.
Like, is it reasonable? Is it rational?
So for your other plots, the only force that you have is just the wind force that's reflecting.
Yeah, I can show you what that looks like. Right.
Okay.
So that's all that's being applied basically.
Okay.
So then I'm running it under aluminum and steel. So
Yeah.
this is the aluminum case, and then this is the steel case.
Right.
So you're seeing a higher concentration of deformation.
Yeah.
Towards both sides of the
Okay.
right.
Yeah.
So you're farther out.
Sure.
But for some reason, with their configuration, it's just one side of the blade.
What's the magnitude though? Let me see. Right now, this is about 0.5 millimeter. What's the magnitude in the other cases?
I think in this guy is like 0.4.
Okay, so it could
Oh,
be,
0.2, and then I think this one's 0.8.
or show me, so the third configuration is at the same material as the second.
Yes.
Okay.
It is.
So it looks like that over here, you're getting the same deformation as you did before. It's about like blue, so it's like around like 0.2.
Yeah.
It's just that this is deforming a lot more, because you're kind of pushing down on it. Where, so that you're pushing down it right here.
Yeah. I can show you. I think that.
I guess that is interesting, that it's only biasing this one side.
Right. Which is a little bit interesting.
Some load is being applied right on the middle.
Right. I mean, it makes sense for it to, to have like a rainbow color and white, but for it to be concentrated primarily on the left hand side.
I'd be interested in seeing, because I get the other surprising thing is that in your base case, you're even getting a lot of deformation here at all, because the force is all being applied here.
Yeah.
And so I'm wondering what direction it's facing. If you can go back to your previous simulations,
Yeah.
or even enhance this, then
If you try to open it on, because I haven't.
okay.
So,
I'd be interested to see what direction it's actually deforming, because right now you're just seeing the magnitude of the deformation. But if that let's just go back to that for a second. You can check it later, but like right now the load is just coming in from perfect. And so if for some reason if this end of the beam is deforming up this way, it's hard to tell from this that this is just the magnitude.
Yeah.
And if the force that's being applied up is like kind of stabilizing that, it's kind of pushing it back down, that might make sense, but I'm not sure why it's being pushed up like that. Because the force is going this way.
yeah, basically. I never applied to them on this side. It's just all.
It is interesting that it's being that side is pushed. I think that's more interesting than the other side. I'd be interested to see what direction. I mean, maybe we can take a look at that together.
Yeah, sure.
See what direction it is, and reading it together. But
Yeah, I'll pull it up.
yeah,
And I
the setup-
appreciate it.
yeah, the setup looks fine to me though. And so I think it's just kind of interpreting the results.
Yeah.
And so,
Okay, cool. Thank you.
okay. I mean, what?
That's fine. That's fine.
If it gets into like 30 or something.
Oh,
like this,
no,
then
that's
fine.
fine.
But yeah, 14 is
All right.
yeah. We wanted to look at the magnitude, right?
Max, yeah, it's weird because I did the same axis here. Just can't pull down. Works perfectly fine.
Okay.
And that small information compared to the other one where it's
Yeah, there's a little pattern.
yeah, and compared to this one where it's fixed against the one here. There's no right on top.
Yeah.
Definitely. Well, I fixed it, so it's no one here.
Okay.
But still,
Still long.
Okay. I even tried to do that little format. They just try to do design so you don't get inspired.
Yeah.
So it could be like a little less form or something. It's still large.
It looks smooth, so I don't think it's not a numeric. When you see the stress distribution.
Correct. Actually, like different boundary conditions, still pretty much.
So it's the same. It's the same magnitude of force if you just really by the page. It's just
Yeah.
I mean, that's in what direction is this one?
The same one. I did do wait a little bit.
Yeah.
It might be,
Why is it it's bigger than I thought? It's almost like three, so let me go do the lecture and then we'll come back after that.
yeah, I think.
Yep, he's here. Yeah. You're one.
All right, it's 5:30, so let's go and get started. Good evening, everyone. How's everyone doing today? Doing good, working on the project. Yeah, so that's due next week. Okay. All right, so first let me say, sorry for a little bit of the confusion at the beginning of class last time. I was a little bit confused about the due date for the problem set, but the email that I sent out, a couple of days ago or yesterday, hopefully that clears everything up in terms of, when that's due and when the midterm is going to be. Okay. And so midterm is going to be, basically the last class session we have right before Thanksgiving, which works out great for me because then I can grade the exams for Thanksgiving break. And then, you'll have the grades, when you come back. Okay. All right. So the plan for today is we're going to do beam equations. Okay. So I'm hoping to make some good progress on the lecture notes today. So I think we should get pretty far. Okay. And then we'll go from there. Okay. I do have your final projects, the specifications ready, just because it's the same specs I've done for, every time I've taught this class. But I know you guys are working on the midterm projects right now, and so I'll refrain from talking about that until you guys turn in the midterm projects. Okay.
Trying to make our heads explode.
Wait a second.
Trying to make our heads explode already.
No, I'm just giving you a heads up. But it's very similar to the midterm project. So I know the midterm project has been a lot of work, but now that you guys have done this, the final project is not that big a step up. And the nice thing about the final project is you can do it on whatever you want. Okay. Okay. So are there any questions I can answer before we get started?
Will we have a final exam as well, or final project?
It's just the final project. Yeah. So the only exam that we're taking is just the midterm exam right before Thanksgiving. Mhm. Yeah, I mean, after all, I think the main point of this class is to learn ANSYS, and so I think the final project should reflect that. It's hard to give an exam for ANSYS. I've tried that in the past, but I've never, no one's ever really been happy with it. All right, any other questions? Okay, all right, so let's go ahead and get started. All right, and we were talking about beam equations. All right, and so we started talking about this a little bit on Tuesday, okay? And it's a beam is basically a structural member that has a different deformations than a truss, okay? Okay. And so in particular, the beams are going to deform in the transverse direction. Okay, and so that's the direction that's perpendicular to the beam. And another type of deformation that we'll consider for beams is rotations. If you recall, before we did ANSYS activity 4, we discussed about how, the thing that's unique about shell and beam elements is that they can include rotations as well. Okay. And that's what you mainly see here. And so visually, it looks like this. Oops. And so here is our beam. And so visually, it looks the same as a truss element. But instead of having displacements that go along the length of the beam, we're going to have displacements that go in this direction instead. Okay. And so those are the transverse displacements. Okay. And the other thing we're going to consider is rotations. Okay. And so basically a rotation is considered a change in orientation of the beam
at those locations. Okay. And so causing these two deformations, we have to have forces, okay? And so we have to have forces in those directions as well that cause these deformations. And so in the transverse direction, we're going to have transverse forces, okay? And so this is going to be F1y and F2y. Okay. And so go ahead and label that. So F1y, F2y, these are transverse forces. Okay. And then causing the rotations, we have moments or torques that we can apply at the nodes as well. Okay. And so this is going to be M1 and M2. Okay. Where M1 and M2 are torques or moments applied at the nodes. Okay.
Dr. Trent, is torque and moment the same thing?
Yes, torque and moment
Okay.
is the same thing. Mhm. All right, and so between these two figures right here, we have kind of our two essential ingredients for a finite element relationship. And so on the bottom here, we have our nodal loads. Okay. Okay. And on the top here, we have the structural response, or these are the structural deformation. Okay. And so the next step is to form the relationship between these two quantities, and that relationship is formed by the element stiffness matrix. Okay. And so I'll go ahead and list that on the next page. And so we're not going to go through the derivation of the element stiffness matrix, just because I want to kind of start getting into the problems. But if you're interested in the derivation, it is available for you in minutes. But I'm just going to show you what it is and just tell you that it's based on Euler-Bernoulli beam theory. Okay. All right. Any questions on this? Okay. So element stiffness matrix. Based on Euler-Bernoulli beam theory, okay? And it connects loads to deformations. That last bit is not unique to beams, right? So all the element stiffness matrices we've seen so far for the springs and for the truss elements, all of those form the relationship between the loads and the deformations. Okay? And so beams are not unique. It's just the way that we derive them is unique. Okay. All right. And so the element stiffness matrix is given by the following. Okay. And so on the one side we have the. Oh, was there a question? Sorry, my mind's playing tricks on me. All right. And so on one side we have the nodal loads. Okay. Okay. And so that's the list of all the loads that we're applying on the nodes. Okay. And so you can see we have the two transverse loads, F1, FY1, FY2, and then we have the two moments, M1, M2, okay? And then we have the element stiffness matrix, okay? And so just to kind of simplify the expressions, I'm gonna go ahead and pull out an expression up front. Okay? And so this expression up front is E times I divided by L cubed. And I'll define what those are in just a second. Okay. And then we have our 4x4 element stiffness matrix. Okay. So we have 12, 6L minus 12, 6L. Then we have 6L, 4L squared minus 6L, 2L squared minus 12 minus 6L, 12 minus 6L, 6L, 2L squared minus 6L, 4L squared. Okay. And this is, of course, going to be multiplied by our vector of nodal deformations. And so we have U1y, theta 1, U2y, theta 2. Okay. And so this quantity that we have in the middle right here, this is our element stiffness matrix for beams. Okay. And so let's go ahead and define what each of these quantities mean. Okay. All right, so first we have E, and so E here is the Young's modulus. Right, so same as it always is. L here is the length of the beam. Okay. And so this newcomer is I, right? And so this is new relative to our truss, where I right here is the moment of inertia of the beam cross section. Right, and so there's our element stiffness matrix for the beam. And so now that we have this, we can go ahead and start using this in problems. And so I have one more quick thing to cover, and then we'll start jumping into some example problems. All right, any questions on this?
Yeah, quick question. So right here, we're in the stationary coordinate system.
Yes.
but-
Well, technically these are in the local coordinates because these are, these displacements are transverse to the beam itself. But we're not going to do any 2D beam problems, and so we're going to assume this is always going to be 1D.
So then, no hat would be needed.
Yeah. Oh yeah. So technically there are hats for this one, but because we're just working all within the same system, then I leave the hats off. Yeah. Mhm.
Perfect.
Yep. Mm-hmm. Okay. All right. So let's talk just really quickly about constraints one more time, and then we'll jump into a problem. Okay. Because now that we have these rotations, we have to introduce a new type of constraint. Okay. Well, it's new for it's new for these kinds of problems, but you guys have been using it this whole semester with ANSYS, and that's the fixed constraints. Okay. All right, and so a fixed constraint, visually, I'll make it look like this, where it looks like the beam is like literally stuck into a wall, okay? And so what's unique about the fixed constraint or the fixed support is that it's going to constrain all the deformation components, including the rotations, okay? Okay. And so we call this node node 1. And what we say is u1x is equal to 0, u1y is equal to 0, and theta 1 is also going to be equal to 0. Okay. Right, so keep an eye out for what supports are going to be fixed, because the supports that we have been using, which are the pins and the rollers, these ones do not constrain rotation at all. Okay, and so if we have a beam that maybe looks like this, and we have a pin support on this side, okay. And so the pin support is going to constrain any displacements, and so u1x and u1y are going to be 0, okay? But theta 1 here is going to be free, okay? And so that goes the same for a roller support too, okay? And so because a pin, even though the pin itself is fixed in place, it's pinned to the beam, and so the beam is still kind of free to rotate around that pin. And so that's important. And so, now that we have beams here, we're gonna do combinations of different constraints. And so you want to make sure that you knock out the right degrees of freedom, and you don't kind of unintentionally get rid of some ones. All right. Any questions on this? Okay. All right. So let's do an example then. All right, so let's consider this this simple beam, a simply supported beam. Okay. I'm sorry, it's not simply supported, but it's because it has a fixed support on one side. All right, so let's say that we have a beam like this, okay? And so on one side, the beam is going to be fixed. By the other side, we have a pin support, okay? We're going to break up this beam into two elements. And so we're going to break it down the middle just like that, okay? And so we have 2 elements and 3 nodes. Okay, so the node on the left is going to be node 1. The node in the middle is going to be node 2. And the node on the right is going to be node 3, okay? We'll call this element A, B. Okay. We'll assume each of the elements have the same length, and so they're going to have a length L each. Okay. And they're going to be subjected to loads being applied at node number 2. Okay, so we have 2 loads. We actually have 2 loads that we're going to consider. Okay. And so we have a vertical load of magnitude P. Okay. And we're going to apply a twisting moment at the node with magnitude M. Okay. And we're going to assume that both elements have the same Young's modulus and the same moment of inertia. Okay. And so A and B are basically 2 identical beams. They're just connected to each other. Okay. All right. And so for this problem, I actually don't have any numbers, but we'll walk through the whole process of setting up the finite element problem. Okay. And so this example right here, I think is a good example for what I would expect you to do on an exam. Okay. And so on an exam, for these kinds of problems, I'm not going to expect you to solve the whole problem, but I do want you to set it up as far as you can go, until right before you can solve it. Okay. And so I think doing a problem in symbols like this is a good way to kind of show that whole process. Okay? And so one way that we can describe it is we can say that, we want to basically set up the global linear system for solution. Okay. All right. And so we're gonna go through our usual finite element process. And so our process, remember, begins with the element stiffness matrices. Okay. And so the element stiffness matrices in this case are going to be a little bit boring, just because they, we're doing everything in terms of symbols. But let's go ahead and write it down anyway. Okay. And so for element A, we have a element stiffness matrix. And so out in front, we have EI over L cubed. Okay. And then we have all the entries in our matrix here. So we have 12, 6L, minus 12, 6L, okay, 6L, 4L squared, minus 6L, 2L squared, minus 12, and so on and so forth. You can see that I obviously don't have this memorized because it's kind of big. All right. And so the element stiffness matrix in this case is not that interesting because it's basically the exact formula that we had before. We can't even plug in numbers. But what's going to be important here is to correctly specify what degrees of freedom this element is working on. Okay. And so since this is element A, we can see that element A is working on nodes 1 and 2. And so let's list out all of the degrees of freedom associated with nodes 1 and 2. Okay. And so we have U1y, theta 1, U2y, theta 2. Okay. Right. And so this thing on the right, at least for this problem, is going to be the most important because it's going to tell us where to insert this element stiffness matrix into our global system. Right, and so I'm going to go ahead and do the same thing for element B. I'm not going to write out the entire matrix again, but it looks identical to the one above it. Okay. But then element B, element B here is acting on different nodes. And so element B is acting on nodes 2 and 3. And so we have U2y, theta 2, U3y, theta 3. Okay. Okay. Right, and so now that we have the element stiffness matrices for both of our elements, then we're now ready to assemble that into the global linear system. All right, question. So that center matrix is the default values. Yes. Yeah. And so those are the default values for for a beam. Oh, sorry. This should be 6L. I think my stylus kind of crapped out. Okay. And so, I think the next problem will have numbers, I believe. Yeah, the next example problem that we do will have numbers. And so, if you have numbers for these problems, you would just basically plug them in and you get values for all of these numbers. Okay. Just, even though, we have this EI over L cubed factor out in front, and technically, that multiplies through everything. When you're working these problems through by hand, I would actually recommend that you keep the EI over L cubed on the outside, just because otherwise it's going to get really messy writing in all these values in the matrices. And so keep it in the outside, but just remember that when you go to assemble, to properly account for that factor. Okay. All right. Any questions on this? Okay. All right. So now let's move on to assembly. Okay. And so at this point, you know, it's the same finite element process that we've been doing. Okay. All right. So we have EI over L cubed out in front. Okay. Then our global system here is going to be a 6x6 because we have 3 nodes. And since we have 2 degrees of freedom per node, it's a 6x6 system. Okay. And so I'm going to go ahead and draw in the labels for all the columns. And so you don't have to do this first, you know, the labels like I do, but I like to do it just to help keep myself organized. But you know, once you start getting good at these, then you don't have to do these anymore. Okay. All right, so let's do element A first. So element A we know works on nodes 1 and 2, right? And so element A is going to go in over here. Okay, and so it's going to take up these 16 spaces. Okay. Element B is going to take up nodes 2 and 3, and so it's going to be these spaces right here. Okay. And so we only have some overlap right in the middle. All right, so let's go ahead and fill in all of the terms, and just remembering that this EI over L cubed is out in front. Okay. Also, you don't want to forget about him, and so when you actually go start plugging things in, don't forget about the guy in front. Okay. I still do it out all the time, but you don't forget him. Okay. Okay. And so those are all the entries from element A. And so we're going to add the entries to element B now. Okay. All right, so first we're going to tackle the overlapping elements or overlapping entries. Okay. All right. So remember, when you have entries that overlap, you just simply add their values together. Okay. And then we have all the other entries as well. So let me just go ahead and quickly fill those in. All right. And then all the entries that don't have a that are not in a box, we're just going to put 0 there. Okay. Okay. So that's the assembly of our global matrix. Okay. And so let's go ahead and combine these terms in the middle here, okay? And so in the upper left middle overlap, we have 12 plus 12, and so this is going to be 24. Okay. On the top right one, we have minus 6L plus 6L, and so that's going to give us 0. Down here, we have a minus 6L plus 6L, and so that's also going to give us 0. And on the bottom right, we have 4L squared plus 4L squared, which is 8L squared. Okay. Okay. And so there is our global system. Okay. All right. And so the last thing that we can do with this problem, since we don't have any numbers, is to apply our boundary conditions. Okay. And so first let's apply our constraints, right? And so for our constraints, we know that node 1 is at a fixed support. Okay. And so since node 1 is fixed, this tells us that u1y is equal to theta 1 is going to equal to 0. Okay. And so that's going to make us knock out the first 2 rows in our matrix. Okay. And so we're going to replace that entire row with zeros, except for ones on the diagonal. Okay. Okay. Meanwhile, node 3 is pinned. And so if node 3 is pinned, this tells us that u3y is equal to 0. Okay. And theta 3, because it's a pin joint, theta 3 is still going to remain free. Okay. And so we're not going to change the theta 3 row, but we are going to change the u3y row. And so once again, we're going to change that entire row. We're going to put zeros on all the terms except for a 1 on the diagonal. Okay. All right, and so the last thing we have to do is we have to put in our loads. Okay. And so we don't have room here, and so I'll do it on the next page. But the loads are going to take place on these 2 rows. Okay. Because remember, the loads are being applied on node 2, and so one of the loads is a downward force, the other load is a moment, and so we're going to apply that on those 2. Okay. All right. Any questions on this before we write out the forcing vector? Okay. All right. So let's go ahead and write out that forcing vector then. Okay. So remember, our forcing vector started out with this. We had all these entries that we needed to specify. Okay. All right, and so the first 2 entries are going to be 0 because those are our fixed constraints. Okay. And so will our last 2 entries because of the pin support and also the fact that there's no moment being applied on node 3. Okay. Right, and so first thing we'll do is F2y. And so since we have a load that's being applied in the negative y direction, we're going to specify that as negative P. Okay. And the moment that we're applying is going to be applied on the theta 2 row. Okay. And so we have an M right there. Right. And so those are our external loads being applied on node 2. All right. And so at this point, if we had numbers for the Young's modulus and the moment of inertia and the loads, we can go ahead and plug all of these in and plug it into MATLAB and solve. But since in this case we don't have any numbers, this is as far as we can take it. Okay. And so the stopping point for this problem is going to be this one, right? And so first we have our forcing vector, and then the other deliverable from this problem is the global stiffness matrix, which is what we got here. And so once these two matrices and vectors are set up, then you're good with all the setup. Okay, because at this point, you would turn it into MATLAB, or whatever other computer software you use to solve equations, and then you can solve for the deformations. Okay. All right. Any questions on this?
Yeah, quick question. So that counterclockwise is positive moment?
Yes. Yeah. Counterclockwise is positive. Mm-hmm. We might write that on this page. Okay. All right. Any other questions on this example before we move on? Okay. All right, and so that's the basics of beam equations. Okay, and so again, the process of solving all these problems, maybe you're getting sick of them at this point, but the process is all the same. The only big difference between all the different methods is what do you plug in for the element stiffness matrix. And so the beam has its own element stiffness matrix, but once you get used to using that, then the whole problem solving process is the same. Okay? It's lengthy, but at least it's the same. All right, and so next thing I want to talk about is reaction forces for beam elements. Okay. All right, and so if you recall from our truss equation unit, we had a way for us to compute what are the reaction forces at all of the constraints in our model. Okay. And remember that these constraints, or or I should say these reaction forces, are needed in order to keep the system in static equilibrium, right? Because if we have a beam, right? And so let's say that we apply a moment, I'm sorry, if we apply a force in that direction right there, okay? In order for this beam to be in static equilibrium, or in other words, in order for the beam to not start deforming, not start translating, then there has to be an equal and opposite force being applied at least somewhere else on the beam. Okay. And so if this beam is fixed to this wall right here, okay, then this wall is going to exert a reaction force just to make sure that this beam stays in static equilibrium. Okay. And so that's that's kind of the reasoning behind why we have reaction forces. Okay? And so the way that we compute these is exactly the same way as from trusses, from our truss unit. Okay. And so the way we do this is after we compute our deformation solution, and so after we perform that calculation, and so basically after we take the last example problem and put it in MATLAB, we can then multiply this by our global stiffness matrix, the one that we had before we applied boundary conditions. Okay. And so exact same process as we had before. Okay. And so, if you want to do it for the last problem, you would take your solution for u1y theta 1, u2y theta 2, u3y theta 3, and then multiply that by the global linear system, after you've assembled everything. And so, after you've inserted all of the element stiffness matrices in there, but before you apply the boundary conditions. Okay. And so there's really nothing new there. And so it's kind of the same as we had before. Okay. But I did want to talk about, a little bit more intuition behind this, just so that you can kind of check your results. Okay. All right. And so whenever you get a non-zero reaction force, it can be in one or two situations. Okay. Okay. And so the first way that you can get a non-zero reaction force is if you have an external force actually being applied on that node. Okay. Okay. And so if we take, node 2 from our previous example, right? So node 2 had a vertical force applied to it, and it had a external moment applied to it as well. Okay. And so if you computed the reaction forces in this for that node, then you should get exactly that external force and that external moment. Okay. All right. And so the other way that a non-zero reaction force can occur is if that node's degree of freedom, or that degree of freedom in particular, is constrained by a support. Okay. And so if we were to compute the reaction forces in the previous problem, node 1 should have a reaction force on both of its degrees of freedom, and because both u1y and theta 1 were both constrained. And the other place where you could have a reaction force is on node 3, but only for the transverse deformation, not the moment. Okay. Right. A convenient way that you can sum this up is that you should only get reaction forces on the places where you apply some kind of boundary condition, whether it be a load or a constraint. Okay? And so if you have a load or a constraint applied at a node, then you should get a non-zero reaction force at those locations. Okay? All right. And so the reason I'm kind of telling you this logic is you can use this to kind of check your results. Okay. And so if you get let's say that you get a deformation solution, and then you use that deformation solution to check the reaction forces. And if the reaction forces don't fit these criteria, where if you have like a non-zero reaction force at a node where no boundary condition is applied, then that's usually a good indication that you should probably go back and check your results, because maybe something was up there. Okay. All right. Any questions on this before we do another example? Okay. All right. So let's do another example. Very slightly more complicated, but at least this one has numbers. Okay. All right. So once again, we're going to look at a two element beam. And so just like before, I'm going to label this node element A. We'll call this element B. Okay. But in addition to this, we're going to have a spring here. Okay. And so the spring is going to act perpendicularly to this. Okay. Okay. And the spring is going to be element C. Okay. I'm going to label the nodes 1, 2, and 3 like before. And since we have an additional node here for the spring, we'll call that node 4. Okay. All right, so let's put some numbers on this. And so the first thing we're going to need are the lengths of the two beams. Okay. Right. And so first of all, we can say that the lengths are going to be 3 meters. Okay. And so we're going to say that these beams have identical lengths. Okay. And we're going to say that they have the same material properties as well. Okay. And so let's say that the Young's modulus is going to be 210 gigapascal. Okay. I here is going to be the moment of inertia. It's 2 times 10 to the minus 4 meters to the 4th power. And since we have a spring here, we also need a spring constant. And so the spring constant for that spring is going to be 200 kilonewtons per meter. Okay. And so in terms of loads, we only have one load that we're going to apply. And so we're going to apply a vertical load P, and that vertical load is going to have a magnitude of 50 kilonewtons. Okay. Okay, and so we're going to take this problem and we're going to compute the nodal deformations and reaction forces. Okay, and so we're going to go through the entire direct stiffness method again, but this time we're going to have numbers ready. All right. Any questions on the setup for the problem? Okay. All right, so let's go ahead and start running. Let's go ahead and start running through. Okay. All right, and so first thing we're going to do, just like the first thing we always do, is we're going to set up the element stiffness matrices for all the elements. Okay. And so let's go ahead and set those up. And so we have element A. Okay. Oh, unfortunately, I didn't plug in the numbers for these ones too, but you can plug in the numbers for these. And so I did these in terms of symbols again. And so we have EI over L cubed. Okay. Which you can compute. And so E in this case is 210 gigapascals. So we have 210 E9. Okay. I here is 2 times 10 to the minus 4. So it's going to be 2E minus 4. All divided by L cubed. And L cubed here is going to be 27 meters cubed. Okay. And so whatever that quantity is, you can plug that in and see. Okay. All right. And so the entries inside here is going to be the same as our usual beam. And so we have 12, 6L, minus 12, 6L, okay, 6L, or L squared, minus 6L, 2L squared, minus 12, minus 6L, 12 minus 6L, 6L, 2L squared minus 6L, 4L squared. Okay. And this is acting on nodes 1 and 2. So it's going to be U1y, theta 1, U2y, theta 2. Okay. Where all the L's that you see in here, you're going to plug in 3 because the length of each of those elements is 3 meters. Okay. All right, and so we can do the same thing for element B, and so element B has the exact same properties, and so numerically, you know, they're all going to be the same in here, but the node that element B works on is slightly different. Okay. All right, any questions on this? Yeah.
Yeah, there's actually 27 meters cubed.
Yeah, 27 meters cubed because we have this is L cubed on the bottom, so we have 3 times 3 times 3.
Okay, I thought that was squared.
Oh yeah, it's cubed. Mhm. Okay. All right. Okay, so let's go ahead and do the other elements. Okay. And so KB here is going to be the same, and so I'm not going to rewrite it again. Okay. Okay, so element B here is going to act on nodes 2 and 3. All right, and then finally we have element C, and so element C here is our new guy. Okay, and this is simply just a spring. Okay, and so we can use our spring element stiffness matrix. Okay, and so remember our spring element stiffness matrix is K minus K minus K K. Okay, right, and then we're going to multiply this by the 2 the 2 degrees of freedom that it acts on. Okay. And so normally what I would do here is I would actually do this in full 2D. And so I would actually use my transformation matrices and make the 4x4 element stiffness matrix. But I'm going to do a little bit of a shortcut here. Okay. And so since the spring is perfectly vertical, that means the compression and extension of the spring matches up exactly with the transverse deformation of the beam at that location. Okay. Okay. And so what we can do is we can just use our usual 1D spring here, okay? And just say that this is going to be acting on U3Y and U4Y. Because normally, if we treated this as kind of a general 2D truss or general 2D spring, we would have something like this, right? So we have K, and then we have our element stiffness matrix here. So we have cosine squared. I think it was a cosine sine minus, yada, yada, yada. I already forgot what the expression is. Okay. So normally this is what you would do, and you would say theta here is equal to 90. Or I guess in this case it would be 270 because it's, the lower number node is on top. But since the spring is already kind of are oriented with that beam deformation, then we can just go ahead and skip that and just do this guy. Okay. But just going to save us a little bit of writing just by observing what a key feature of the problem. Okay. All right. Any questions on this? Does that make sense? Why we why we would make that simplification? All right, question. Our question is the beam stiffness matrix a constant for all beams, regardless of cross section? I beams, rectangular, angle bar, etc. No, it's a good question. And so the it would be different. It would be different for the different kinds of beams, and the way that it would be reflected are in different kinds of moment of inertia, right? And so the effect of the shape of the cross section, whether it be I beams, L beams, angle beams, that's going to be reflected in I. It's not a perfect representation because it's definitely possible for two beams of different cross-sectional shapes to have the same moment of inertia. That's definitely possible, but it at least gives you a pretty good first approximation. Okay. Yeah. Our question. So would that constant of EI over L cubed be multiplied by as well for KB and KC? Yeah. So it would be for KB. And so if KB, remember, is also a beam. And so for KB, we have the EI over L cubed here. Right. But since element C is a spring, then we just only have the spring constants. And so we don't have this constant out in front. Yeah. Yeah. So I think this is the first time where we're really mixing a lot of different element types. And so you want to make sure that you have all your constants correct. And you don't put any extra constants in there. Yeah, it can be tricky, and so make sure you're doing these problems kind of carefully and kind of methodically. Yeah.
So then for this specific problem, or for any, you can have any type of element, and we would just have to be careful based on what you just said.
Exactly. Yep. So you can mix trusses, beams, springs. We're not going to do frames, but frames are possible too. But yeah, you can mix and match all the different kinds of elements. It's just you have to be mindful of what constants you should put in there and what direction it's facing as well. Yeah.
And also another question back to the note that you mentioned earlier. So that if we were to have the spring horizontal to the beam, then we would have to worry about the cosine and sine.
Yeah, it's a good question. And so if we have the spring this way instead, then the spring would want to deform this way, right? This would want to go to the left, or it would want to go to the right, right? And so actually, this is actually a problem that we can't actually solve in this case, because the beam is going to want to go up and down because that's what it's designed to do, or at least that's what we're assumed to do. But the spring wants to go left and right, and so there's kind of a mismatch here between these two. And so if you had a situation like this, for element B right here, you would either have to use a frame element, which can deform in all different ways, or this B element would have to be a truss, and so that it can actually compress and expand. Okay. But because we're assuming the beam can only go up and down, then there's going to be a mismatch if the spring was horizontal.
So you can have like a truss to the end of the beam and a spring to the beam.
Yep.
I mean a spring to the truss.
Yep.
Okay.
Yeah, it can get pretty wacky sometimes, and so especially with frames. And so the most general thing is if you have a node here and you can say that it can deform in every single direction, and that's what a frame is. But the math for that definitely gets messy. Yeah, it takes up an entire page. It takes me an entire page here just to write the element stiffness matrix, because even though this one is 4x4, a 4x4 is not that bad because we have 16 total entries here, right? And so we count four rows, 4 columns. For a frame, each element stiffness matrix is 6x6, and so it literally takes me like probably 10 minutes each time that we have to write one. So it's not fun. I've only ever done that to my grad students, and even they were not happy with it. Yeah. Okay. All right, so those are the element stiffness matrices, and so now let's move on to assembly. And so assembly, it's the same as we always do, okay? Except now we have an extra degree of freedom for node 4, okay? And so our matrix this time is going to be 7 by 7. There's no theta 4 because node 4 is only attached to the spring, and so there's going to be no rotation there at all. Okay. And I know that U4Y is ultimately going to be 0 because it's a fixed support. But I did want to include it in the assembly because I want to show you how I assembled that beam or that spring. Excuse me. Okay. And so first thing we have is element A, right? So element A is nodes 1 and 2. Okay, so element A, just like it always is going to be just like this. Okay. Element B is nodes 2 and 3. Okay. And so that's going to be just like this. Okay. And so here's the interesting one, element C. Okay. Element C is a spring. Okay. And so remember, a spring can't rotate. Okay. And so a spring can only expand, compress, and expand. Okay. And so the only degrees of freedom that element C are going to modify are going to be U3Y and U4Y. Okay. And so we're going to skip over theta 3 right here because the spring has no influence on that rotation at all. Okay. Okay. And so the spring element is going to be that entry, this entry right here. Okay. I drew it a little bit too big. So this should just be on U4Y, U3Y. Okay. It'll be this entry right here and this entry right here. Okay. And so we skip over all the rows and columns associated with theta 3 because the spring can't influence that at all. Okay. All right. Another way that you can check, especially when you have kind of a disjointed element stiffness matrix like this, is to count all the squares that you included. Okay. And so our element stiffness matrix for a spring, if we can go back to the previous page, we can see has 4 entries in total. Okay. And so there should be 4 entries in the assembly where this is applied. Okay. And so you can see we have 1, 2, 3, 4. Okay. And so we're good to go. Okay. Right. Because when you're doing disjointed element stiffness matrices like that, then it can be easy to kind of lose track of a term or maybe or kind of highlight one term or one section more than the other. And so the easiest way is just to count it up and just to make sure that you have the right number there. Okay. All right. And so let's go ahead and start filling these in. Okay. And so just to save some space, I'm going to say that we have our factor of EI over L cubed out in front. Okay. And then let's go ahead and start. Let's go ahead and start filling these in. Okay.
Question.
Yep.
would that just only be applied to A and B, not to C, or would it still be applied to all of them?
Good observation. And so when we get to element C, then you'll see how I apply that there. But you're absolutely right. And so it should only apply to A and B. But it's a lot more work to not put it out there. So I'm going to put it out in front, and then we'll adjust for it on C once we get there. I'm going to go ahead and just combine the overlapping areas for A and B, just because this is the same as our earlier example. Okay. Okay. And so in the overlapping parts, we have 24, 0, 0, and 8L squared. Okay. Then we have all of the element B contributions. I'm going to skip over the box where it overlaps with. Actually, no. Let me put in the contribution from element B first, right? Because for element B we just have a 12 there. All right. And so those are all the contributions from elements A and B, and so those are the same as our first example. Okay. Now we come to the contributions from element C. Okay. And you know, just like someone pointed out, you know, element C doesn't have this EI over L cubed in front. Okay. So element C is only going to be contributing K. Okay. But you know, to save us a lot of work, you know, we put that EI over L cubed in front, and so what we're actually going to contribute here, and let me put it in this bottom right one just to make it a little bit more clear, is we're going to do K, okay, times the inverse of this entry here. So we're going to do K times L cubed divided by E times I. Okay. And so when you multiply, you know, this whole entry here in the bottom right, multiplied by the factor out front, you just get K, right? And that's what you should get, because you know the spring is only contributing just K. Okay. All right, so let's go ahead and fill in the rest of this. And so it's going to be a little bit tight in here. And so it's going to be 12 plus KL cubed divided by EI. Okay. Here we have a minus K L cubed divided by EI. Okay. Then here we have minus K L cubed divided by EI. And of course, you know, everything else here is zeros. Okay. All right, and there is our global system. Okay. Right, and so the next step is going to be to apply boundary conditions. Okay. And so let me, oh, that's supposed to be open. Oh, that's weird. And so let me say that, you know, in the lectures, I'm saving time by just kind of overwriting the entries on this matrix with the boundary conditions. But when you're working on this on the homeworks, you know, don't lose this matrix, because this matrix as it is right now is really valuable, because remember, this is what we're going to use to compute reaction forces. Okay. And so don't lose this one. And so, you know, for now, I'm just going to be overwriting this just because it's, you know, it's just because we're under the constraints of the classroom. But trust me, when you do your homework problems and if you overwrite this, you're going to regret it, because you're going to get to the next part of the problem and it's going to ask you to compute reaction forces. And you're going to be like, and I have to recompute this whole thing all over again. So, you know, so don't lose this. And so, you know, save this and then just write the version with the boundary conditions maybe below it. Okay. All right, but with that said, you know, let's go ahead and do our boundary conditions now. Okay. And so we have three constraints here. Okay. First, we have a fixed constraint on node 1. And so we're going to circle this row and this row, and then do our usual thing. Okay. And change these rows accordingly. Okay. The other boundary condition that we have is a fixed constraint on node 4. Okay. Okay. And so updating this for the fixed constraint on node 4, we have the that thing right there. Okay. Okay. And our last boundary condition here is our load, which we're applying vertically on node 3. Okay. And so we're going to have our load of P applied here. Okay. In fact, it's going to be minus P. All right. Okay. And so now that we've made our changes for the element stiffness matrix for the boundary conditions, excuse me, we can go ahead and plug this into MATLAB and solve for the deformations. Okay? And so we're gonna get 7 deformations here, and so we're gonna get all 4 U's and 3 theta values. Okay? And solving a 7x7 system is that's definitely much easier to do with MATLAB than it is by hand. Okay. All right. Any questions on this before we write out the solution? Okay. All right. So we plug this into MATLAB, and then we get a solution, and we end up with the following. Right. So we get U1y is equal to 0, theta 1 is equal to 0, and so that's expected because we have our fixed support there. Okay. Next, we have U2y, and so U2y is going to be minus 0.02 meters. Okay. And theta 2 here is going to be minus 0.612 radians. Okay. Right. And so here's a big an important point. So whenever you solve for theta in your in these beam problems, the units for that is going to be radians. Okay. U3 is going to be minus 0.0638 meters. Okay. Theta 3 is going to be a minus 0.016 radians. Okay. And U4y is going to be 0 because it's a fixed support. Okay. Okay. And so those are all your deformation values. Right, and if we do a sanity check really quick, we can see that our maximum vertical deformation is at U3y, right? At least in terms of magnitude, and that makes sense because that's where we're applying the loads. Okay. All right, and so before we head out, I know we're just about out of time, but let me go ahead and write out the reaction forces. Okay, and remember the way that you get the reaction forces is you take your deformation solution above, and then you multiply it by the global linear system before you apply the boundary conditions. Okay, and we end up with the following results. Okay. Okay. And so we have interesting reaction forces on node 1 because that's where we have our fixed support, right? And so we have a good reaction force there. Node number 2 doesn't have any boundary condition applied to it, and so it shouldn't have any reaction forces at all. Okay, and so we have 0 newtons and 0 Newton meters for F2y and M2. Okay. Okay. For our node 3, we have our external load being applied there. And so we have a minus 50 kilonewtons because that's our external load. But there's no external load on the rotational component. And so we have M3 is equal to 0. Okay. And then finally, we have the reaction force on the bottom of the spring. And this is the last piece that we need to, in order to get a, static equilibrium, static system. Okay. And so we get F4y is equal to 12.77 kilonewtons. Okay. All right. Okay. And so there's our solution. Any final questions on this before we wrap it up for the week? Okay. All right, and so that's all we got planned. And so this is our last class session, or I guess technically Tuesday is the project's not due until Tuesday night, and so I'll see you guys on Tuesday before the project's due. But I am going to stick around today after class. I know I've already kind of agreed to talk to a couple people after class today, and so if you have questions on the project, you can stick around. And I'll come, answer all the questions that you have. Okay. But if not, if you don't have any questions, then hope you guys have a good weekend. Best of luck, everyone working on the project. Shoot me an email if you have any questions, and I will see you guys next week.
Professor.
Thanks, guys. Oh yes, happy Halloween, everyone too. Yeah, have a good Halloween. I totally forgot it was Halloween.
Thank you, Professor. Have a nice Halloween.
Thanks, you too.
Hello, Professor.
Hang on, there's a question in the class first, and I'll come back.
You can go ahead.
Okay, all right, go ahead.
I had a question on the assembly matrix.
Yeah,
So when you applied the minus P, that whole U3Y row,
Yep.
minus P.
So when we apply the loads, remember, we don't actually modify the matrix, but the P just goes into the right-hand side forcing vector. And so I didn't have room for it here, but remember there's another vector on the right-hand side of this. And that's where the P goes. But we don't actually change any of this at all. And so this all stays the same. It's just that the P goes onto the right-hand side.
Okay, got it. Thank you.
Yeah. Kevin, question?
Oh, yeah, just going back to the reaction forces. So the reason why the F1y and F4y, they don't add up to 50 kilograms is because the moment kind of takes some of that into account.
They should add up to 50. We have 37.23 plus 12.77. So we have 0,
Oh, yeah, I'm
0.
sorry.
Yeah, 50. Yeah. Yeah. So there is, it does look like the moment is unbalanced because there's no other moment here. But that external force also produces a moment because the beam has some length. And so I think if you do 50 kilonewtons multiplied by the length of the beam, then that's then that's kind of what you get for the moment. Yeah.
Okay. I think I switched up the 37 to 27.
Oh, I see.
Okay, thank you.
All right, so let me go ahead and answer project questions. And so if you're on Zoom and if you have questions on the project, just kind of hang tight. Now I'm going to do a round around the classroom and then I'll come back. Okay.